Today we are going to look into knapsack problem using the method branch and bound. If you have not yet subscribed, please do subscribe, and if you like our video, like it, and any comments or any improvement, please do add it in our comment box so that we would improve it later. Okay, so let us get into the problem. Branch and bound is the method, and we are going to solve the problem which is going to be called as a knapsack. As we have already discussed about branch and bound, you can refer to the earlier video where we have spoken about the state space tree, and we have dealt about backtracking and the basics of branch and bound. So as you will be knowing that branch and bound and backtracking are face to face with the help of state space tree. Okay, let's get into the concept knapsack problem. It is a common problem where we have a capacity W and there are n items, and the known facts are going to be the weight and the value for each and every item. So this n items, and we have weight Wi. So I is going to range from 1 to 12. How many ever items are there, we will be having so many weights with respect to the item and the value for each item. So it is going to be in an order that the first item is going to be of more value, that is the value divided by the weight, and the second item will be less than or equal to that of the first item, and the last item is going to be the least of all in the case of this branch and bound. So we have already looked into the concept of state space tree. So state space tree is going to be a tree structure where all the states are going to be indicated, and here the branching takes place and the bounding factor is being determined. So depending on the condition, whether it is going to be the minimum or the maximum, we decide whether it is going to be the lower bound or the upper bound. So in this problem, knapsack problem, we deal with by getting the maximum profit to be filled with the capacity W, with the items which are available and the weight and the value which are being given. So since it deals with the maximum, here we have the upper bound which will be estimated. So here upper bound is being estimated by the value plus the capacity minus the weight which is going to be related to that particular item into, that is multiplied by the next profitable value. Okay, so this is going to be the actual value, and this is going to be the prediction which is going to take place for the future. Okay, so we know these things. So knapsack problem is we have a sack for a container with a capacity of W, and there are n items which are available in the real world, and we know the weight and the value for each and every item. And here for this branch and bound, we arrange it in this way that the first item is of a larger value and the last item is of a smaller value. So we use the concept of state space tree, and the branching takes place depending on the bounding factor, whether it is going to be the maximum or the minimum. We decide whether it's going to be the upper bound or the lower bound. Here in this problem, it's going to be the upper bound. So we have the actual value and the prediction value as such. Let's go to the example so that you will understand it much more clearly. So this is an example. So here we have 4 items, and we have weight for each item which are being indicated, and we have the value for each item which are being given. So now we have to calculate the value by weight. That is, value is going to be 40 and weight is going to be 4. So this value would be 10. Okay, so here it is 42 divided by 7, so it will be 6. Here it is 25 divided by 5, so we have 5, and here 12 divided by 3, that is 4. So these are the inferred value. So this is going to be the constraint. So the first value 10 is greater than 6, the second value, and 6 is greater than the next value, and 5 is greater than the last value. So this condition has been satisfied. So now we have a capacity of W equal to 10. Okay, so hope you can match what is W, the capacity equal to 12, 10, and whatever number of items are going to be 4. Okay, so we have I ranging from 1 to 4, and we have Wi here, Vi here, and we have Vi by Wi, which is given V1 by W1, V2 by W2. This is going to be V3 by W3. This is V4 by W4. Hope it is clear and there is no doubt for you. Now we have to calculate the upper bound. So since it is going to be the maximum value, we are going to calculate the upper bound. So if it is for the minimum, then the calculation would have been for the lower bound. But here, since the profit has to be maximum in the case of our knapsack problem, we calculate the upper bound. So upper bound is given by this formula. So this is going to be the first state where there are no items added. So if there are no items added, the weight would be 0, and no items, so weight would be 0 and value also would be 0. So here we have 0 as the value. So now the upper bound has to be calculated. So what is the formula for calculating the upper bound? So upper bound is the value, this value, okay, plus what is the formula? It is W is 10 minus small w, that is this value, and this is going to be multiplied by I plus 1. That is, here we have V as 0 and W as 0. So plus 1 would give you V1 by W1. So V1 by W1 value is 10. Okay, so now this value is being taken into. So 0 plus 10 into 10 is going to give 100. Okay, so the present value here is 0 and the prediction is going to be 100. Okay, so now how do we branch and go? So it is going to be with item 1 without item 1. Okay, so with item 1. So what is the weight for that? It is going to be 4. What is the value? It is going to be 40. So how do we calculate the upper bound now? So upper bound, V is equal to 40 plus this value 10 minus, what is the weight now? 4. So that is the weight. Then this has to be multiplied by, it is now V1 by V2, sorry, W1, which are available. So if I am going to add 1 here and 1 here, it's going to be V2 by W2. What is V2 by W2? It is 6. So here we have 40 as, here another 6 and 6. This will give me 36. So 76 is going to be my value here. Okay, so here I am not adding the first item. So the weight is going to be 0 and the value is also going to be 0. So when the weight and value are 0, now let me calculate the new upper bound. You might be wondering, weight and value are the same, but how can the upper bound, why should I calculate it? It will be same as 100. No, please listen to this. Okay, so here the new value is going to be 0, and my capacity is going to be W10 minus 0, and here we are in a state V1 by W1. So if it is going to be the next one, it's going to be V2 by W2. So V2 by W2, what do we have here? It is 6. Okay, so now 0 plus 10 into 6 will give us the value 60. Okay, so now as we go down, we will be adding the next item with item 2 without item 2. So with item 2, okay, so now already we have 4, and now when we add this item 7, what would be the answer? It is going to be 11. So what happens when the capacity or the weight becomes 11? Now we have the capacity 10, so 11 is more than 10, so the sack cannot proceed further. So we cannot go through this path. So since we don't have a solution, or we cannot go further in this, we stop at this level saying that I cannot have my container filled more than 10, and now it is 11. So we stop at this particular level, and we almost like backtrack and get back to the path where we will get a solution. So now here we are not adding the second item, so it is going to be the same 4, and we are going to have the same value 40. So now hope you are familiar and you can help me more with the solution. Now the value is going to be 40 and W is going to be 10, and I have this weight 4, and what would be my new V3? 2 plus 1 by W2 plus 1, that is V3 by W3 value. So what is V3 by W value? It is 5. So what value do I have? So it is 6 into 5, 30 plus 40. I have 70 here as my upper bound. Now here the next branching factor is going to be with item 3 without item 3. So item 3. What is item 3? So item 3 weight is going to be 5. So now already I have 4 and 5, which is going to be 9. Does it satisfy the condition? Whether it is less than 10? Yes, I can move further. So here I have this 40 as the value, and I have a new value of 25. So my present value is going to be 65. So this is how we go about it. So can we calculate the new upper bound for this particular case? So the new upper bound is going to be 65 is going to be my value, okay, this value which I have, plus W is going to be 10, and now I have already had a new capacity of 9. Okay, so what am I going to multiply with? So the multiplication factor is going to be 4. That is V4 by W4. So what would be my value? So now I have 65 here and I have 1 left here multiplied by 4, that is 69 I have as my value. So now here, if I don't have any weight, or if I don't add the third item, what would be my weight? It will be 4 and my value would be 40. And if I have to calculate the upper bound, the value would be 40V plus 10 minus 4 into 4. So I have 4 here, then 6, 4 are 24, and I have 64 is my upper bound here. Now adding the last item with item 4 without item 4. So now what would be the value of this weight? Already I have 9 and the weight for this is 3. So this would cross the limit as opposed to 12. So now can I add this item? No, I cannot add further. So I have to stop with this. So here what would be my weight now? It is 9 and the value is 65. So what do I do now? I have to calculate the upper bound. So upper bound is going to be value as 65 plus 10 minus 9. And what is going to be after this? Do I have a V5 by W5? No, I do not have another item here. I do not have another item. I do not have another item too. So there is no value at all. So if there is no value, then we have it as 0. So my upper bound is going to be 65. Okay. So now let me look into this part. So now my maximum is 65 in this particular group. So this 65, I take it and I compare here. So when I compare here, I find that 65 is more than 64. So 65, I take it as the optimum. So here, this one, I find 65 more than 60. So I conclude that this 65 is my optimal solution. Okay, so now my solution would be, my bank will get the maximum profit with this item number 1 and without the item number 2 and with the item number 3 and without the item number 4. I would get a good profit which is going to be maximum, that is going to be 65. Okay, so now I have got the solution. So this is the best solution which I have got through the method which is called as branch and bound. I have solved for the problem which is knapsack. Okay, so just a summary of what we have learned. Knapsack problem, with n items and weight and value are known. We arrange it in order that the first item is with the maximum profit and the next one at the last item. We use the concept of state space tree, branch and bound. We branch it in such a way when if we don't get a solution, we go back to the previous and try to find another solution. We have a bounding factor which is going to be either lower bound or upper bound. So depending on the solution or depending on the problem, whether we need a minimum answer or maximum, we decide on. Here in knapsack, we need the maximum, so we stick on to the upper bound. So upper bound is being given by the formula V, actual node value, and it is going to be a predicting value for the future nodes. Okay, so this is going to be the capacity. And this was the example. We calculated V by W, and we started with the 0 node by adding the first item or without adding the first item. We just calculated the upper bound and we found out which has the most value. We just dragged it down, and if that was the constraint which is not being satisfied, that is overseeding the capacity, we stopped in that particular level and we went back to the next level. So here we just went step by step, and when we found that here we have a comparison 69 and 64. 69 is bigger, so we move this part so that we will get maximum profit. So here in this particular level, when we came, there are no more items to be added, and we find that the prediction gives us there are no more profits, so it results in 0. So the actual value is going to be the upper bound. Okay, so comparing this value with the other values which are present, though the predictions are there, the actual value is more than the predicted value. So we conclude that this is the optimal solution of all the parts. So this is the concept. So we have the branch and bound method introduced, or it is being solved by having a state space tree, and this state space tree will determine which node or which part is going to give us the maximum profit. Okay, hope you understood this problem and hope you understood how to solve that this knapsack problem by using this branch and bound method, and hope you will be able to solve the other problems in a similar way. So if you have any comments or any recommendations, please do pass it in the comment box. If you like our video, please do like it and tell your friends too. And if you have not yet subscribed to our channel, please subscribe. Happy learning. Have a good time.